So we have a scenario here where there's a 5 kilogram object sitting on a ramp, and our goal is to find the acceleration of this object, okay, and as it slides down the ramp. And so for the first part, we'll assume there's no friction acting and see how we do, and then we'll go ahead and add a component which we have to worry about friction too. Okay, so when we set this up, remember we're going to draw a free body diagram. So downward we have the weight equal to mg. We have the normal force acting parallel to the ramp, or perpendicular ramp, sorry. And then right now there's no friction, so these are the only two forces acting. So what we're going to do is we're going to draw a net force equation, and before we do, we're going to kind of reorient the coordinate planes. We'll call this x, and we'll call this y. And we'll say that this way is positive x. That means it's going to slide in the negative direction. Okay, and then if you remember from before, this angle then would be equal to 20 degrees. And so we could say, okay, let's find the net force for the forces acting in the y direction. Okay, which actually we don't even need here, right? We don't need to know the normal force, but if we want to find it, we could do this. And so in the y direction, it's balanced. It's not going to fly up off. The normal force is preventing it from falling through, so it's balanced in that direction. So acceleration that way would be 0, and the net force that way would be 0. We have the upward normal force, and then the downward component of gravity that's pulling it into the ramp, which is the part that would be along this axis. So this would be mg cos theta. Okay, so that's mg cos theta right there. So the normal force equal to mg cos theta. Theta is 20 degrees, g is 9.8, and the mass is 5 kilograms. So if we want, we could plug that in and simplify. Okay, but we're going to continue on. We're going to solve for acceleration. So to do that, we need to find the sum of the forces acting in the x-axis, which this will not add to be 0 because there's nothing holding it in place, nothing preventing it from sliding. And so what's going to happen here is that we're going to say, well, this is going to add to be equal to m times a, and this is a for this kind of x direction. Okay, you can put an x there if you want. So in this case, we only have the one force pulling it down the ramp. This would be this part of gravity right here, which would be mg sine theta. And as you can see, this is the negative direction, so this would be negative. Okay. Now something interesting is going to happen right here. You're going to notice m is on both sides of this equation, and so the m will actually divide out. So ax would be equal to negative g times sine of theta. So what we can conclude from that is that the mass actually doesn't affect the acceleration here. Okay, and so in this case, it's going to slide down at that same rate regardless of how big it is, as long as, now the key here is that there is no friction. Okay, when we go ahead and look at friction, it's not going to be the same. Okay, so we go ahead and punch this into our calculator, and we get that a is equal to negative 3.4 meters per second squared. Okay, so acceleration negative 3.4 meters per second squared. Okay, so let's go ahead and do this again, but let's say this time there are 10 newtons of friction pulling it up the ramp. Okay, so when we draw our free body diagram, it's going to look a little bit different. We have normal force, but this time we have some friction. We'll say it's kinetic friction since it's sliding. Then this is equal to 10 newtons. We still have weight pulling it straight downward, and we're going to rotate that coordinate plane again, 20 degrees. Okay, this is x, this is y. So for this one, the normal force isn't going to change. Gravity's pulling it down the ramp with the same amount. The ramp's having to balance it with the same amount. So normal force will be the same. But now when we write our equation for the net force, we're going to say that ma for x, so the sum of the forces for x, it's going to be equal to now this 10 Newton frictional force minus the mg sine of theta. Okay? which means that A is going to be equal to 10 newtons minus mg sine theta all over m. We can simplify a little bit and say that, okay, 10 over m minus g sine theta. Okay, so we know from before that g sine theta was 3.4, so this is minus 3.4 meters per second squared, and then 10 over the mass is 5 kilograms, so this is going to be 2. Okay, and so basically that friction is going to take away 2 of those meters per second squared, and so now we only end up with negative 1.4 meters per second squared. Okay, alright, we're going to do this one more time, but in this case what's going to happen is that instead of there being friction, we're going to have another mass involved. So we have this block sitting on the ramp. Okay, and this time there's a mass connected hanging right here. Okay, this one will say has 5 kilograms of mass. This one will say has 2 kilograms. Okay, now this situation is a little bit different than the situation with the friction. Okay, yes, we have 2 kilograms of mass. Actually, let's change it. Let's say it's 1 kilogram. Okay, so let's say we have 1 kilogram of mass, which would be the equivalent of 1 newton of force. 10 newtons of force. However, why would this still be different from the last situation where we had that 10 newton force of friction? What's the difference here? Or what do you think that difference might be? The difference in this case is that the total mass of the system has increased. We have a greater total amount of mass that we have to accelerate, which means that so like in the case of the friction, we just had to overcome that force. Not only do we have to overcome the downward force here from gravity, in addition, we also have to accelerate this mass along with that one. Okay, which means that it's going to have a little bit less acceleration because of that. So let's say that this way is positive. Okay, and we're going to do net force equation. Again, we're going to ignore the y direction this time. We're going to say it's balanced, like we showed that first time. So we're just going to do net force in this direction. For that 5 kilogram mass, now we have weight downward. We have the normal force this way, and then now we have tension pulling it up. Okay, for this hanging block, we have weight downward. We'll use big M for the 5 kilogram block. We use little m right here, and then we have tension pulling back up. Okay, so we're going to do 2 net force equations in that plane of motion. We'll start with this one right here. So we'll say the sum of the forces acting in that x direction for the 5 kilogram object is going to be big M times A, which right, M has to add up to be MA since it's accelerating. We have down the ramp that component of gravity, which was mg sine theta, so we have negative mg sine theta, and then pulling up the ramp we have tension. For the other block, we'll do the sum of the forces in that same plane of rotation. So this is for big M, this will be for little m. They got to add to be MA, and then we have gravity pulling it downward in that positive direction, so little mg, minus in this negative direction we have tension pulling it that way, so minus t. Okay, and so now we want to solve again for A, so we're going to add these together. Okay, and what we get is big MA plus little ma equals negative mg sine theta. The t's are going to eliminate, t and negative t is 0, and then plus little mg. Okay, we can factor the a out from here, so we get m plus m times a, and then we'll divide that over to the other side, so we get that a equals negative big mg sine theta plus little mg all over m plus m. Okay. And so here we're dividing by 6, and whereas before we divided by 5. And so that's the big difference. So this is going to be equal to 6. We'll say again that this is equal to 10, and this was, I believe, let's look back. That one was negative 3.4. So this is negative 5 times 3.4 meters per second squared. Okay, so 3.4 times 5 would be about negative 17, okay, plus 10 all over 6 kilograms. So these are newtons, kilograms. Okay, so we're going to get negative 7 newtons over 6 kilograms, which divides out to be, let's see, negative 1.17 meters per second squared. So what you can see here, acceleration was a little bit less. We have a slightly more mass here. Before the acceleration, when we had the frictional force of 10 newtons here, the acceleration in that scenario was negative 1.4 meters per second squared. And here it's now 1.17 because we're also having to accelerate that hanging mass too. Okay, and since the system has more mass, that means it's more resistant to having acceleration. Okay, hopefully this made sense. Please let me know if you have questions.